Module A1, the chemical level of organization. And Objective 3 states that a student should be able to define matter, elements, and isotopes, and identify each subatomic particle based on structure, location, charge, and mass. Since this is one of the first objectives in a video lecture, let me just say that our exams in this course is objective driven. So if the objective asks you to define matter, I would definitely look that term up in the glossary of the text and write out the definition and learn it. Because when we get to the first exam, those are the types of questions that you'll see. We will expect you to have a working definition of matter, of elements, and of isotopes. Matter is anything that occupies space and has a mass. In general term, for a substance of which all physical objects consist, everything physical on Earth consists of matter. Matter, if it's broken down to the simplest form, we find atoms. When we look at the periodic table of elements, this represents all the matter on Earth. In fact, if you were to look at Earth, you would find about 90 elements represented. If you were to sit down and take the time to count the elements on this periodic table, you would note that there are more than 90, and that's mainly because some of these elements, especially these very heavy elements, they were man-made in laboratories, so that they're not natural on Earth but man-made in a laboratory. So we have about 90 elements comprising the Earth, and of those 90 we will find 25 elements within our body, and we'll look at those prominent elements in a minute. Back to atoms, and again, atoms are the simplest form of matter. If you take matter and break it down to the smallest particles, you are going to find atoms. Atoms themselves are comprised of three subatomic particles: the proton, the neutron, and the electron. Within the core of the atom, the center of the atom, you're going to find protons and neutrons, and here we specify that these are found within the nucleus of the atom. Protons have a positive charge, often noted by a little plus sign representing a positive charge, and they have an atomic mass of 1. That is their mass. Neutrons, also found in the nucleus, they are neutral, and they're also going to have an atomic mass of 1. That leaves electrons. Now, electrons are not found within the nucleus. Instead, they are found orbiting the nucleus within the electron cloud. And here we see a representative electron pair orbiting the nucleus. Here's one electron, here's the other. Electrons have a negative charge. In fact, I often represent electrons with this symbolism, with the little negative sign and the letter E. And they have a very, very low mass. In fact, with all respects, it's almost insignificant. Very, very tiny subatomic particle. Electrons are constantly in motion around that nuclear core, around the nucleus of an atom. And let's stop here and think, what would keep electrons orbiting around the nucleus? Well, hopefully you've come up with an answer that of charges. We know that protons are positively charged and electrons are negatively charged, and in the famous 1980s lyrics of Paula Abdul, opposites do attract. So the electrons are physically attracted to the protons. That negative charge is physically attracted to the positively charged protons in the nucleus. And that is what holds atoms together. That is what keeps the electrons orbiting around the nucleus of the atom. Now that we have some atomic structure down, let's look at some nomenclature, some numbers that are often represented on the periodic table of elements. If you look at a periodic table of elements, and you could easily Google this or find a copy in a text, what we have is a chemical symbol. And some of these chemical symbols are relatively straightforward. If you consider carbon, the chemical symbol for carbon is C. Here we have Na, and this is the chemical symbol for sodium. In terms of the numbers, the periodic table gives us an atomic number. Atomic number represents the number of protons, and if that atom is stable, it's also going to represent the number of electrons. So, if we were to take a sodium atom, how many protons would we expect to find in the nucleus? The answer is 11, because that is what the atomic number dictates. If that atom is stable, how many electrons would you expect in the electron cloud orbiting the nucleus? If you have 11 positive charges within the nucleus, you would have 11 negative charges orbiting the nucleus to maintain stability. The positive is going to cancel out the negative charges. So that atomic number gives you a lot of information. It gives you the number of protons and the number of electrons if the atom is stable. We also have a number often at the bottom or underneath the symbol on the periodic table of elements called the atomic mass, or the mass number. And this represents the number of protons plus the number of neutrons. What is the weight of a proton? 1 atomic mass unit. And the weight of neutron is also 1 atomic mass unit. So the atomic mass is going to represent all the number of protons plus the number of neutrons. And if you look at sodium, you'll get a number like 22.99. And I know this doesn't make complete sense, but when we discuss isotopes shortly, hopefully we'll shed some light on that. As promised, here is a short list of the elements found within the body, within a human body, by percent of the total body weight. So what this means is that oxygen comprises about 65% of our body weight. We are large sacks of water, and we know that oxygen is one of the prominent components of water, just for example. Other key figures: carbon and hydrogen, nitrogen, calcium, phosphorus, so on and so forth. At the bottom of this table, we have a list of trace elements. These are elements found in very small amounts. We have a little bit of aluminum in our bodies, a little bit of cobalt, a little bit of copper, for instance. I'm not expecting you to memorize this list in any way, nor am I asking you to memorize the percent of total body weight, but you should be able to come up with these heavy hitters. You should know that oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus are represent a large component of our body, or large composition of our body. Alright, let's go back to elements and isotopes. Elements are determined by the atomic number of an atom. And if you remember, the atomic number represents the number of protons found within the atom. And we find that elements are the most basic chemicals. And again, if you think of back to the periodic table of elements, those are all elements. Let's look at isotopes. Isotope is a particular version or variant of an element based on that mass number. And let's reproduce something we've already seen before. This chemical symbol represents what? Na. It represents sodium. Does anybody remember the atomic number of sodium? The number of protons found within the nucleus? What else does that atomic number indicate? I'll give you a minute. Actually, about 2 seconds. The atomic number also indicates the number of electrons if an atom is stable. And if you remember, the atomic mass of sodium is 22.99, and this is where we're going to try to explain where that 22.99 comes from. The atomic number represents the number of protons plus the number of neutrons. How many protons does sodium have? It has 11. We are told directly by the atomic number. So we have 11 protons, and obviously this atomic mass is suggesting that we have extra neutrons. In fact, if you were to take 22.99 and you were to subtract 11, let me just write protons here, you would find that 11.99 represents neutrons. And this is where isotopes come into play. Isotopes are particular atoms in which the neutrons differ in number compared to that of the protons. So that the particular atom is slightly heavier. In fact, if you were to take all the sodium on the Earth, you would find that most of the atoms will have 11 protons and 11 neutrons. But there's a small percentage of sodium on Earth that has 12 neutrons or 13 neutrons. And if you take all of those atoms combined, you get an average mass of 22.99. And that's where you get a little bit of variation. And we're not going to work with isotopes very much in A&P, but you should be aware of what an isotope is and how we get to these atomic masses.